What's this? Please, silence. Can you get out of the screen? Oh, thank you. That's much better. Oh, hey, what's wrong with you? Can you please get out of the screen? Thank you. That's much better. Well, this is a binary optimization example, and I have called it the animals at the farm. Well, we need to assign 6 different animal species, cows, chickens, ducks, geese, peacocks, and rabbits, into 4 different portions of land. Under these conditions, these will be the constraints of the problem. First of all, take care that geese and cows cannot live together in the same place. So, we are expected to avoid cows and geese to live together in the same portion of land. Up to 2 different animal species will be placed at the same portion of land. And additionally, I don't want any portion empty. So every portion will have between 1 and 2 animal species. Finally, their span life, the life expectancy, is respectively these years. But this information is not useful. It's only for misleading. So we will not use this because it's not leading us to a new condition. So the portions of land assigned will not depend on the life expectancy of each animal species. So first of all, we will define the optimization array. It will have 24 elements. Why? Because we have 6 animal species and 4 candidates for the portions of land. So the meaning for every element in X, as you can see, X is a column array. The meaning of every X is the following. The first 4 elements belong to coals, and it means, the first one means coals in portion 1. You remember that it's a question because every element in the optimization array is a binary element. So at the beginning of the simulation, we don't know if x1 will be equal to 0 or 1. That's false or true. So we don't know at the beginning. The aim of the problem is to find the values of all the elements in X, being all of them false or true. Depending on the cost function, and on the constraints. So the second 4 elements belong to the chickens, assigned in portion 1, 2, 3, or 4, as you can see here in the table. Cows, chickens, ducks, geese, and so on. So, for example, X23 means rabbits in portion 3. We don't know if at the end this will be 0 or 1. It will depend on the solution of the problem. Well, what about the objective function? Because we don't have a best solution. Why? Because we don't have any preference. We don't have any vet's opinion, any farmer's opinion. We don't have preferences at all. So all the elements in the cost function will be equal, will be 1. Remember that the cost function is a linear combination C1, C2, C3 until C24, because we have 24 elements in the optimization array. that multiplies every element in the optimization array. So these 24 elements means how good is to put x1 equal to 1, because at the end f is equal to c1 multiplied by x1 plus c2 multiplied by x2 plus c3 multiplied by x3, and so on. So every coefficient means how good is to put a 1 here for the solution of the problem, for the maximization or minimization of the cos function f. MATLAB only needs this, all the coefficients. What about the equality constraints? To be sure that all the animals are assigned to a portion of land, we will do the following. Pay attention. Here we have the equation for the cols. That means cols in portion number 1, cols in number 2, cols in 3, cols in 4. I'm forcing that one out of these 4 variables are equal to 1, because all of them can have a value 0 or 1. So I'm forcing that only a single number in here can be equal to 1. All the 3 others must be equal to 0. I don't know which will be 1. It will depend on the cos function and on the constraints. The same goes for the chickens. But as you can see here, I have added 4 positions in the array, because every animal is 4 positions long. So, how can I tell this to MATLAB? At the end, as you can see, I have 1, 2, 3, 4, 5, 6 constraints. Here we are, constraint number 1, 2, 3, 4, 5, and 6. This is a SPI A equality 1. As you can see here, I have a coefficient of 1 for x1, that's this element. I have a coefficient 1 for x2, that's this element, x3, this element, and x4, this element. For the second equation, I have added 4 positions, so it begins at 5 and it ends at 8, as you can see here, and all the remaining ones. Finally, here, that's the figure for SPI B equality 1, which is equal to 1, 1, 1, and so on. What about the inequality constraints? The linear inequality constraints are of this kind. But as you can see, for every portion of land, I have a minimum of 1 species and a maximum of 2 animal species. This x1 means cols in portion number 1. That's why, because I am talking about portion number 1. As you can see here, cols in portion number 1. What about the chickens in portion number 1? Is x5, as you can see here. What about ducks in portion number 1? 9. So what I'm telling here, that maybe 1 or 2 coefficients or elements in the optimization array can be equal to 1. All the remaining ones will be equal to 0. So maybe this and this will be 1, maybe only this, I don't know, but I'm forcing that a minimum of 1 element out of these 5 positions in the optimization array will be equal to 1, or maybe a maximum of 2 elements out of these 5 elements in the optimization array will be equal to 1. The same goes for portion number 2, portion number 3, and portion number 4. Here you can find how I have done this in the MATLAB environment. But pay attention, MATLAB only understands this kind of inequalities. So these kind of inequalities are forbidden in MATLAB. So nothing to add in this less or equal than 2, because all of them, this part of the equation of the inequality remains the same. Why? Because at the end is that less or equal than. But the problem is here, because this addition must be greater or equal than 1. So I need to turn this into a less or equal than. How can I do that? By changing the sign into a -1 for all the elements in the equation. So that's the way I have turned a greater or equal, because here are the variables, greater or equal than 1. Now the variables with this sign change are less or equal than -1, not +1. So at the end, cols and g's cannot live together. So for portion number 1, these are cols in number 1, as you can see here, cols in number 1, and x13 are g's in number 1. So I must force that this addition is less or equal than 1. This way I'm forcing, or I'm avoiding, to both have a number 1. So with this equation I try to avoid cols and g's in the same portion number 1. The same goes here for portion number 2. I have cols in number 2, g's in number 2 is x14. If I add these 2 elements and I force them to be less or equal than 1, I'm forcing that maybe both are 0, maybe 1 is on x2, maybe 1 in x14, but 1 cannot be in both. So it will not be true to have cols in number 2 and g's in portion number 2. So the same goes for portion number 3 and portion number 4. And that's how I have written it. I have coded it into the MATLAB environment. Finally, I have done the compilation of all the inequalities. Here, can you see here the inequality constraints, and here the single set of equality constraints. The cos function, remember, because this cos function has no preferences, it's what I have called a constraint satisfaction problem, because we have no best solution. Any solution that satisfies all the constraints is good for us. So I called in linprog with the cos function, can you see here? Then I tell that all the 24 elements are integers, integer linear programming, integers, all the elements in the optimization array from 1 to 24, then inequality constraints, equality constraints, and this is the lower bound set, and this is the upper bound. Thanks to this 124, I know that all the x are integers, okay? But integers is not the same as binary. So when I put the lower bounds equal to 0 and the upper bounds equal to 1, means that x will be 0 or 1, false or true, binaries. And then finally, a possible solution is this. And you can see that coals and rabbits are not living together. But it's only a possible solution, not the best, because there is no best solution.